Section 4.1 is maximum and minimum values of functions. So this will be one of the key components that we work with, or key elements we work with for much of chapter 4. Maximum and minimum values of functions provide us with optimal values for functions, right? So if we have a function that models something realistic, like a cost or a payoff in some sort of situation, like maybe a business function or a cost and energy function for some kind of engineering problem, we might want to minimize the cost of energy, or we might want to minimize the cost in dollars in a financial problem, or maximize the payout for a financial situation. So, and these apply to all kinds of different applications, but that's later on. We need to talk about what is the maximum or minimum value of a function. So if we let C be a real number in the domain D of a function f, so C is some real number for some set of numbers that's the domain of function f, then f of C is the absolute maximum value of f on this domain if f of C is greater than or equal to f of x for all x and d. It's exactly what you'd expect. It's the absolute maximum if it's greater than everything else. Here's a sketch of a function whose domain is all reals and has an absolute maximum at some value c. This we'll say is the point c, comma, f of c. It has a maximum at x equals c, and that value, the value of that maximum, is f of c. It's the top of the parabola here, if this were a parabola, right? Kind of assuming it more or less is. So that is a sketch of that. Notice that this function, right, this point is greater than, it has a y value, right, an output value, an f of c that's greater than any other x value on the curve, right? If I put another point down here, this is another x comma f of x on here. Of course, f of c is greater than f of x, right? It's above this y value down here. Okay, so that's the idea of an absolute maximum. We could reverse all of this and talk about c being an absolute minimum for this function, or for a function, if we had a function that looked potentially something like this, right? So I'm drawing functions that are smooth and differentiable. It's another world. It's kind of out of our scope in calculus if we talk about something like an absolute value function that's shaped like this. This does have an absolute minimum, but we can't find it with calculus, really. And we'll see more or less why that's the case in just a little bit. So a local minimum or a local maximum is a situation that might look like this. Right? Now we'll note that this is just some arbitrary curve. Looks like it's a cubic polynomial potentially, or the graph of a cubic polynomial. A local maximum, f of c, or the number f of c, is a local maximum if f of c is greater than or f of x when x is near c. Okay, so let me see. A local maximum in this graph is sort of king of the hill, right? We have this little spot here. This is c1, f of c1 as a point. The local maximum value is f of c1. It occurs at the value x equals c1, right? So this is a local maximum. And we could see why it's a local maximum, because near it, we just go like nearby and just a little ways away, maybe as far as this on either side, we see that it's above all the values that are near it. Okay. Eventually, though, if we look over here, it's not an absolute max or a global max, because if we go over here, we tie that value and then we move above and we're greater than that value. So this function actually doesn't have an absolute maximum because it trends onward towards infinity in this direction. So it doesn't have an absolute max, but it does, however, have a local maximum right here. Oftentimes, we're interested in local maximums for functions, or maxima of function. Similarly, we have a local minimum over here. We might be interested in local minimums for functions. We'll call this one C2 and f of C2. And if you realize that if we just look nearby, just move a little bit left, a little bit right, cut that off right here and here, and we realize that this is the lowest point, or the least y value in this little nearby range. It's the sort of the unking of the valley, I guess, whereas the other one was king of the hill. I don't know. It's the lowest point. Okay, so those are our absolute maximum, sometimes also called global max and min versus our local max and min. All right, so let's get to work with some problems here. First example says determine the maxima and minima if they exist of the function y equals sine of x. So y equals sine of x. What we remember from that is it's got a bunch of local maxima and local minima, right? It's a waveform, moves up and down, right? So it's got minimums here, it's got maximums here, and it's going to continue to have maxima, minima as we move left and right. There are infinitely many of those. So the idea is to identify what they are. The absolute maxima of this function are y values that are 1. It's the largest this function ever attains, and it attains its absolute maxima, and it's absolute because the function's never larger than that. This is the largest value the function ever attains, even though it does it infinitely many times. Well, this happens at x equals pi over 2, and then it happens for every 2 pi k lengths away from there. So I add 2 pi k, where k is any integer, right, to this. And so it also happens at pi over 2 plus 2 pi. It happens at pi over 2 plus minus 2 pi, or pi over 2 plus 4 pi, which is 2 times 2 pi, and so on. So we capture all of those values in that way. Remember what we've done here, recall trigonometry, what we've done is we've solved the equation sine x equals 1. Well, that solution is this one right here. Okay, so that's all that's really happened there. For the absolute minimum, we realize that, well, it has absolute minima, it has infinitely many of those, and that's when y is equal to -1. That's the smallest value y equals sine of x ever attains. We set sine of x equal to -1, and we realize, okay, its absolute minima are values of y equals -1, and they occur at these values once we solve for sine x equals -1. K is any integer, of course. So there's our y equals sine x, maxima and minima. They're absolute. Okay, so they're also, coincidentally, each of these is also a local max and a local min, right? So that's kind of interesting that they coincide. They won't always coincide, but sometimes they do. Determine the maxima and minima if they exist for the function f of x equals x squared. So we're looking for any kind of absolute maxima or minima, and we're looking for any kind of local maxima or minima. So let's see. Y equals x squared. Remember, its graph looks something like this. It does not have a local maximum. It always grows larger and larger. We can always find a larger value above it somewhere. So there is no local maximum. There's no absolute maximum either. Okay, there's no top of a hill anywhere, and there's no largest value that this function attains because it just keeps getting larger indefinitely. However, it does have a local minimum down here. Down at the bottom, at the vertex of the parabola, it's the lowest point in a valley, right? So it is a local minimum, but also, if you look at this function and consider it, not only is it a local minimum, it's an absolute minimum because it's the lowest point overall for this function. So it's a local minimum and an absolute minimum. Typically, when something is also an absolute minimum, that's a stronger condition. So we'll call a minimum that's absolute an absolute minimum rather than calling it a local minimum. Okay. The value of the local minimum is y equals 0, and it occurs at the value x equals 0. Remember, that's the vertex 0, 0. So x 0, comma, y 0, right? Okay, so that's our parabola. Okay, next, the third example down here. Determine the maxima and minima if they exist of the function g of x equals x. Well, this is the line y equals x in its graph, right? This thing has no absolute max and no absolute min, right? It continues on indefinitely this way, so it'll always attain a larger value than anything you could list, and it could always attain a lower value or a smaller value than anything you could write down. Now, does it have a local min or a local max? Well, no, it doesn't have any valleys, it doesn't have any hills. So it has no absolute max, no absolute min, no local max, and no local min, interestingly enough. Same thing, actually, too, if we think about the cubic function, which looks something like that, right? This thing doesn't have local max or local min. There are no hills or no valleys. There's almost, right? Along here, it almost looks like we get the top of a hill, but there's no point that you could pick along here, right? Where that point to the left and to the right is larger than anything or less than everything around it, right? Any point you put on here, you're never at the top of a hill or the bottom of a valley. So we have no local max or local min for this. Since it goes on indefinitely up and down, it has no absolute max or absolute min either. All right, so some interesting theorems involving local extrema and absolute extrema. The extreme value theorem, if we have a continuous function f on a closed interval a to b, then f will attain a maximum value f of c and a minimum value f of d at some values c and d in the closed interval a to b. Okay, we're guaranteed that that will happen. And let's think about why. F is continuous. It doesn't jump. It doesn't have asymptotes. And it doesn't have holes or missing points in its graph. Okay, so if might look something like this. We've just sketched a general version of it. If we have a closed interval a to b, then we're talking about this continuous piece of the curve between a and b here, or a comma f of a for this point, and b comma f of b for this point. Now, somewhere in here, this thing has a maximum value in this interval, right? It looks like it might be here's the maximum value that the function attains right at the endpoint. Another candidate could be here or here. We'd have to test those values if we knew the function to actually decide. The absolute minimum or a minimum on this interval looks like it would be here, right? Again, outside the interval, the function drops down this way, continues indefinitely that way. So there are no maximum, there is no maximum or minimum value for this function on all of its domain. But if we restrict to a closed interval, we're guaranteed that somewhere it will have a max value and somewhere it will have a min value. And if you just think about, if you draw a few more sketches of continuous functions on finite closed intervals like this, I think you'll convince yourself that this must be the case. That's a very useful tool. Furthermore, if f has a local maximum or minimum at c, and if f is differentiable at c, or in other words, f prime of c exists, then f prime of c must be equal to 0. So if this were c, right, and f was a local maximum, then it's necessarily the case that the derivative at this point is equal to 0. Well, if the derivative at a point c here, right, at x equals c, if the derivative of the function is 0, that means the slope of the tangent line is 0. Well, that makes perfect sense. If this is a local max or a local min, the tangent line there needs to be horizontal. Or in other words, the derivative at that point needs to be 0. So this is a very useful theorem for us. We build a definition based on that, and that's this critical number. Critical number of the function f is a number c in the domain of f such that f prime of c equals 0, where f prime of c does not exist. And that's the asymptotic function in a situation where we have a vertical asymptote potentially. And that could tell us something about max or min on an interval. Okay. First things first, we'll find the critical numbers of a given function. This is usually as easy as taking the derivative, setting it equal to 0, and finding the numbers that satisfy that equation. In other words, writing f prime of c equals 0 or f prime of x equals 0 and solving for x. We're looking for all the numbers c that satisfy this equation. So I take the derivative of this function. F prime of x is just through power rule on this polynomial, 3x squared plus 12x minus 15. Now I set this function equal to 0. So here it is, this function equal to 0. Divide by 3 on both sides, right? This will stay 0, and I'll have x squared plus 4x minus 5. It cleans it up a little bit. Since they're all divisible by 3, it'll make trying to factor this easier. Remember that if factorization is difficult or you don't see how to do it right away, you could always use the quadratic formula, or you could complete the square. It's up to you. Quadratic formula is probably the best brute force method to use here, though. So this thing actually does factor into x plus 5 times x minus 1. And we can use the multiplication property of this equation to write that x is equal to negative 5 or 1. We have two solutions to this. It's when x is 1 or when x is negative 5. That's the whole point of factoring and doing all these steps with these things. So our critical points, the points that make the values of x or critical numbers, I should say, of this function, our original function, are the values that make its derivative 0. And we could check if we wanted to. When we plug in -5, we'll get a 0. When we plug in 1, we'll get a 0 as well. So those are our critical numbers for this. Now, our critical numbers are candidates for where we may or may not have local maxima or minimum. So let's have a look. Find the critical numbers of the function, determine whether the function has a local maximum or local minimum at its critical numbers. Here we have f of x equals x cubed. Well, the derivative of x cubed is 3x squared. We set that derivative equal to 0, and we solve for 0, right? So, and 3x squared equals 0. We divide both sides by 3. We have x squared equals 0. Take the plus or minus the square root of both sides of x squared equals 0, and we get x is 0. Right? I think that's pretty obvious that the solution to that was x equals 0 all along. X equals 0 is our only critical number. All right. Now we determine with x equals 0 whether or not this is a local minimum or local maximum. Well, in this case, we'll have more tools later, but for now, in this case, luckily we just remember what f of x equals x cubed's graph looks like. I already talked about it earlier in this video. It looks more or less like this. It has a point at the origin. In fact, that's x equals 0. And it has this end behavior on the left and this upward end behavior on the right. Well, if I look, this is neither a local max nor a local min. I'm a little bit disappointed, possibly, if I was hoping for a local max or a local min. Hopefully, I'm not confused that it doesn't have a local max or a local min. It has a critical number, x equals 0. That's a number that makes its derivative 0. So it's a critical number. Let's go back and look at that theorem. If f has a local maximum or minimum at C, and if f prime of C exists, then f prime of C is equal to 0. What we're doing now on the page after this is the converse. All we've done is we've found a place where f prime is equal to 0. No, 0 actually. F prime of 0 is 0. We cannot assume, we can't go backwards in this theorem. This is the result of the theorem. We can't imply the antecedent from the consequent of the theorem, right? That's the converse. The converse of this theorem is not what's written here, it's this theorem. If it has a local max or minimum and a derivative there, then f prime of that, then the derivative at that point is 0. It doesn't guarantee that if the derivative is 0, that it's a local max or a local minimum. So be very cautious of that. It does give us a list of candidates from which to determine whether or not there are local max or local min. We would conclude in this case that there are no local maximum or local minimum values on this function, right? Just by recalling its graph. We'll have other tools for this later, but for now that's sufficient. So Fermat's theorem, rephrased, perhaps something a little bit more helpful to clarify what's going on here, is that if f has a local maximum or minimum at C, then C is a critical number of f. Again, it's if it has a local min or max there, C is a critical number, right? In other words, C is a place where the derivative is 0. It doesn't guarantee the other way around. It doesn't say if we have a critical number, then it's a local max or a local min, okay? Nonetheless, when we go looking for local max and local mins, we're going to generate all the critical numbers we can, because if there is a local max or a local min, then it's going to be on that list of critical numbers. That's the usefulness of this tool. So here we look at the closed interval method, right? So we're going to employ everything we've done so far, the extreme value theorem, Fermat's theorem with this with local min and local maxes to determine absolute maximum and minimum on intervals. So to find the absolute maximum and minimum on an interval a to b for a function f, or a continuous function a to f actually, we find the values of f at the critical numbers of f on at the critical numbers of f on the interval a to b. Okay, so in other words, find all the critical numbers for f, places where the derivative of f is 0, and list those. Only the numbers between a and b will be valid. Then we evaluate the endpoints of f. That's f at a and f of b. And then the largest value from steps 1 and 2 is the absolute max. The smallest value is the absolute minimum. There we go. So it's that straightforward. Okay, so let's see this in action. This maybe is confusing directions until you see an example of it. Find the absolute maximum and absolute minimum of the given function on the given interval. F of x is equal to all of this on the interval -2 to 3. It's a closed interval, so we can talk about its absolute max and absolute min here. Now, first things first, I want to find the critical numbers. So I'll set the derivative f prime of x equal to 0. Well, I need the derivative first, so let's do that. The derivative here is 4 times 3x cubed, so 12x cubed. This is going to be -12x squared. This is -24x. Derivative of 1 is just 0. All of this is being set equal to 0 because I'm looking for the critical numbers of this function. Now I can factor out, notice I can factor out an x from this equation to simplify things. Really, I guess first I factor out a 12. I divided 12 on both sides. The right-hand side's still 0. And I get x cubed minus x squared minus 2x equals 0. Dividing that by 12. Now, I have an x common to all of these factors on the left-hand side, so I'll factor an x out, and I'll have x squared minus x minus 2, still equals 0. Now I factor x squared minus x minus 2, back in algebra, or I can use a quadratic formula there, and I have x times x minus 2 times x plus 1. I have 3 critical numbers here, 3 places where the derivative is equal to 0. That's when x is 0, when x is 2, and when x is -1. Putting those in order, -1, 0, and 2 are my critical numbers. All right, I don't have any critical numbers that arise from when the derivative is undefined, because this derivative, this function, is not undefined anywhere. It's defined everywhere. It's a polynomial, so it's just fine. I don't have any does not exist critical numbers, so I don't need to list those. So in my interval -2 to 3, all 3 of these critical numbers fit. So I start with my left endpoint, -2, and then I go through all of my critical numbers that are within this interval, -1, 0, 2, and then when I'm done with my critical numbers, I end at my right endpoint, 3. So I've made up the entire list of candidates for my absolute max and absolute min of this function f on the interval -2 to 3. Now I just need to plug these values into the function f to determine whether or not I have a maximum or a minimum there. I'll just compare everything down the list. So I don't use my derivative anymore. I go back to the original function. Be sure to do that. Don't make this mistake of plugging the numbers in here. We're done with that once we find the critical numbers. So f of -2, well, that's 3 times -2 to the 4th, minus 4 times -2 cubed, minus 12 times -2 squared, plus 1. All of that together looks like it comes out to 33. And I continue down the line doing that. I plug in -1 and get -4 up here. I plug in 0. Well, 0 is easy to see. I'm going to get 1 when I plug in 0. I plug in 2 and I get -31. Of course, you can check these on your own if you like. Plug in 3 and I get +28. Now I go through my list and I see what is my largest, what is my smallest value on this list. Whatever my largest value is, it's like 33. That's my absolute maximum on the interval -2 to 3. It occurs at x equals -2. So the max value is 33, and I get that by plugging in -2, by choosing x equals -2. Similarly, my smallest value is -31. And that occurs when I plug in x equals 2. When I choose x equals 2, I get the minimum value. So here's our summary here. And that's all there is to the closed interval test. Find the critical numbers, list them inside the interval -2 to 3, or your given interval, for any of the numbers that fit inside there. Had one of my critical numbers been something like 5, by the way, that's on the other side outside this interval, it doesn't fit on the list. It's not inside the interval -2 to 3. So 5 as a critical number is just omitted. I'm not allowed to use it. It's not in the interval. So that's our closed interval method. And that works for any function, polynomial or otherwise, preferably a differentiable function. It certainly should be at least a continuous function. Okay. So find the absolute maximum and minimum values of the given function on the given interval. This one's a little bit more complicated. We've got f of x is equal to x squared minus 1 cubed on the interval -1 to 2. Well, it's a little bit more complicated looking, but the process is still the same, right? I have f prime of x. I'm going to set that equal to 0 ultimately. But to calculate f prime of x, I need a chain rule. 3 comes down. This power is reduced to a 2. Inside is the function x squared minus 1. I need to multiply that through the chain rule times the derivative of x squared minus 1. Well, the derivative of x squared minus 1 is 2x. So there we go. We've just taken the derivative, maybe some simplifications in order. This is going to turn into a 6x times x squared minus 1 quantity squared. That's exactly what we see here. We're setting it equal to 0, so here it is, set equal to 0. We want to solve for the x values that satisfy this equation. Well, it's pretty easy to see. Divide both sides by 6. We end up with x times x squared minus 1 quantity squared equals 0. We can factor the inside of this. X squared minus 1. Well, that's x plus 1 times x minus 1. It's a difference of squares inside here. It's all still squared, so I put brackets and squared it here. Now I have 3 roots. I have x is 0, x is 1, and x is -1. When I write those down in order, I have the following: -1, 0, 1. Doesn't matter that these roots were squared. I still get a 0 in here, right? I'm looking for whenever the inside of this is 0. Doesn't matter if it's squared or not. 0 squared is 0. So I only need these roots directly. Okay, so moving on. Critical numbers are this list. Now I go through and look. -1 to 2 is the list that I'm looking at. Well, we have -1, and then our critical number is -1, because that first one was the endpoint, right? Well, those are both accounted for then. The next is 0, so I put that on the list. Next is 1, I put that on the list. Notice these critical numbers are still within the interval. They're still less than 2 and greater than -1, or equal to -1. And I end at my right endpoint of 2. So both my endpoints make the list, and any of my critical numbers that are between them make the list. Since -1 was equal to an endpoint, I didn't have to write it a second time. And it sort of automatically qualifies to fit the list because it's an endpoint. Now, f of x, right, is our original function, the very first function we were given, right, applied to each of these numbers. So f of -1, well, -1 squared is 1, minus 1 is 0, 0 cubed is 0. And we go through and continue to plug these in. Plug in 0, I'm going to have -1 cubed, I get -1. Plug in 1, I get another 0, 0 cubed is 0. And then I plug in a 2, I get 4 minus 1 is 3, 3 cubed is 27. So I make up my whole table. Now I can compare everything. The smallest value over here is a -1. That's my absolute minimum on this interval. It occurs when x is 1 or 0. When I choose x equals 0, I get the absolute min. 0, -1 is the absolute min by a point. 0, -1, right? X value 0, y value -1. Similarly, my absolute max, well, the largest value on the right here is 27. So the point 227 is the absolute maximum. When x is equal to 2, we get a maximum value of 27. So there we go. That's another iteration of the closed interval test. That's really all there is to it, finding maximum and minimum values on a closed interval. We'll go on to use more of these properties of local min and local maxes in section 4.2, and perhaps even a section or two beyond that. In general, we're going to be very interested in finding the critical numbers, the places where the derivative is 0 for functions, for lots of different reasons, right? First to sketch graphs, and later to optimize functions of real-life models and other things we might be interested in.